So let's continue our discussion of the free particle. Last time we said that for a free particle, the general solution of the Schrodinger equation is of this form, right? A times e to the ikx plus b to the negative ikx. What was the value? What was k here? Square root of 2me over h bar. And square root of 2me is really just momentum, right? Absolute value of momentum over h bar. And so we said that the momentum is h bar k, right? And the energy is h bar k squared over 2 times m. We can just rearrange these equations. So, we did that already. A lot of energies are h bar k squared. I'm sorry? We already finished all of this pretty much.
We had that one slide last year.
We were starting on this ideal gas molecule, right? We finished the entire, including psi for that one?
I don't think we finished the whole thing.
Yeah, but we did not plot psi. I was meaning to plot psi for that one.
You were trying to show us it.
A plot of psi for this one. Okay, so let's just do this one over, and we'll plot the psi for this one. So let's see. Bring up MathCAD. And zoom in on this. Alright, so let's define our energy. Let's say we're looking at an average helium atom in a sample at room temperature. So the energy is, for the average energy of a helium atom would be 3 halves RT, 3 halves KT. And at temperature T, we're going to assume we're at 298 Kelvin. And we have to tell it what K is. K equals 1.38 times 10 to the negative 21.
That sounds right.
Okay, negative 21 plus Boltzmann's constant times joule per Kelvin. Okay. And what's the mass of our helium atom? 4 AMU.
It's 1.3 times 10 to the negative 23rd.
Okay, so 1 AMU equals, well, 1 AMU is, a mole of AMUs is 1 gram, right? So I could just do it this way. Let's see. 4 AMUs. It's 4 grams per mole, right? Divided by Avogadro's number, that gives you grams, times, that will give you the answer in grams. Right? So we just have to define Avogadro's number, equals 6.022 times 10 to the 23rd per mole. Okay.
Boltzmann's constant is times 10 to the negative 23rd.
Negative 23rd. I could never remember that. I prefer to remember it as R over Avogadro's number. So let me make this. Let me redefine it as R over N sub A. R over Avogadro's number. And R is 8.314 joules per Kelvin per mole. Oops. Let me drag all of this down. R, the gas constant, is 8.314 joule per Kelvin per mole. So let me line these up. Separate regions. Okay. This is our mass. Let's just verify what that mass is. Mass equals 0 kilograms. Okay, we need to set our zero tolerance to, what was it? 10 to the negative 300. Okay, so 6.6 times 10 to the negative 27 kilograms. And what's our energy? 6.171 times 10 to the negative 21 joules. Boltzmann's constant is that. So that's joules per Kelvin. 1.381 times 10 to the negative 23rd. And what else are we supposed to do? So what is our K? K equals square root of 2 times the mass times the energy divided by H bar. I need to define what H bar is. H is 6.626 times 10 to the negative 34 joule seconds, and H bar is H over 2 times pi, right? So that's our K. That's per meter. That should be the right unit, right?
How do we get E?
E. We're just assuming we're dealing with an average helium atom, an average ideal gas molecule at room temperature. At any a given temperature, will have an average energy of 3/2 kT. Okay, that's from kinetic molecular theory. So K is, does that have the right unit for K? Remember our function was e to the I kx and e to the negative I kx, right? So x and k should have reciprocal units, right? So if x is in meters, k is per meter, so you're raising it to a unitless quantity, okay? Alright, so what about our momentum? H bar times k, right? So P equals that. And this is kilogram meters per second. And we said it's moving to the right, right? So it's positive H bar k. Momentum is positive. Alright, so what is our psi again? Little psi equals e raised to the power 1i times k times x, right? This is psi as a function of x. Alright, and what is our big psi? What is our f of t? E to the negative I, so 1i e, right, times t over h bar, right? So IET over h bar. And what is our big psi? Xt equals little psi of x times f of t, right? And so what's the period of the oscillation of this time-independent part? Remember, this is the sum of cosine et over h bar, right? Minus I sine et over h bar. And remember we said before, anytime you have something like that, cosine or sine, okay, it's better to write it like cosine 2 pi t over tau, so you can get the period of the oscillation, or sine 2 pi t over tau. So we can identify 2 pi t over tau as e over h bar, right? 2 pi over tau as e over h bar. So what's our tau then? Oops. Our tau is going to be 2 pi h bar over e, right? 2 pi h bar over e. And so h bar is h over 2 pi, so that's just going to be h over e. And the reason I'm interested in a period of oscillation is I want to show an animation of this function over that period. Okay? So I'm going to define the period of the oscillation Tau is h over e. Right? So what is tau? Tau in this case is equal to 10 to the negative 13 seconds. Okay? Now what would be, if I know this is going to be what? Cosine kx plus I sine kx, right? That's what e to the ix is. So what would be the wavelength of this? The de Broglie wavelength would be equal to what? You can see that k, right, is equal to 2 pi over lambda. Okay? So you write, instead of writing kx, you say 2 pi x over lambda. That's the best way to be able to sketch the function right away. Because then you're going to say, if that's the case, then if I were to plot it right here, from 0 to lambda, I know I'm going to get one cycle if it's a sine wave, or if it's a cosine wave, it's going to be like that, right? So, k is 2 pi over lambda. So what's lambda? K is 2 pi over lambda. Lambda is 2 pi over k, right? 2 times pi over k. So lambda is a 10 to the negative 11 meters. So 7 times 10 to the negative 11. So that's about 0.7 angstroms. An angstrom, if you recall, is 10 to the negative 10 meters. So this is about 0.7 angstroms. Okay. So imagine this helium atom in a 1 meter size, 1 meter length box. Okay. You're going to have, imagine you have a 1 meter box. The wavelength, the period of the oscillation is about a tenth of an angstrom. It's about an angstrom. Okay, so that 10 to the 10th is what? 10 billion, right? A billion is 10 to the 9. 10 to the 10. So imagine you have a meter stick. Okay, the length of your box is length corresponding to a meter. Imagine dividing that into 10 billion parts. You can have 10 billion cycles of the wave within that box. So you can see the wave-like behavior is going to be under these conditions. The wave-like behavior is going to be very difficult to detect. It's almost like the waves the probability of finding the particle within that would be more or less uniform. You're not going to see the oscillations. Well, actually, in this particular case, it is uniform because the integral of the absolute value of psi squared is going to be constant. But the oscillations in the cosine and the sine function are very hard to will be very hard to detect within that interval. Okay. So anyway, let's plot this. We're going to plot it from. Remember, we're not putting any restrictions on psi, right? So let's plot this from x equals. Let's say starting from negative 5 lambda up to 5 lambda. So the first number is negative 5 lambda. The next number is negative 4.99 lambda. So I'm going to plot it versus at 0.1% of lambda in the intervals between the points. And then semicolon gets you to the final, allows you to enter the last number, which is 5 times lambda. I'm going to plot it there, and initially I'm going to assume t is 0. So if I'm going to plot that versus x, and plot that versus x over lambda. Okay, so I'm going to plot psi. What can I plot? Big psi, right? Let's just do little psi first. Little psi of x, and I don't see anything. Little psi is a complex number, right? E to the I is e to the ikx. So I can plot the real part and the imaginary part. So let's plot the real part. The real part of psi of x, and you can see it's better. And what should be the unit for this? Per meter to the 1/2. Oops. Okay. So you can see your sine goes from, your cosine function goes from +1 to -1, right? So let's make this from -2 to +2 so you can see it better. All right. And if I were to plot the imaginary part of sine, meters to the -1/2, and there's your cosine, your sine function. So your sine function starts at 0, right? And your cosine starts at 1. Alright, so let's do another plot here. This time we're going to plot big psi itself. Graph xy plot. Big psi is a function of x and time. And again, it's going to have real and imaginary components. So let's do the real part. With m to the -1/2 and versus x over lambda. Okay, and you can see it's pretty much the same because at t equals 0, big psi is just equal to little psi. You recall? If this t is 0, then this is just 1, so big psi will just be equal to little psi times 1. And the imaginary part of big psi, xt, over m raised to the -1/2 should be the same as this other one. And let's just change the scale. So let's do it from -2 to +2. Okay? So it's the same thing. Let me just drag this one down here. Oh, that's not what I want to show. So let's animate this. Let's see what happens to this over time. Let me show a grid on this one. Grid lines. And I'm going to do 2 cycles. So I'm going to show, I'm going to do, well, let me do, let's see, 10 grids. Okay, let me stretch this one out. Oops, what happened? I need to set the limits here from -5 to 5. There. Okay. So I've got 10 grids. And so this time I'm going to animate this. So I'm going to say t equals frame times 0.01 times tau. Okay, so if I do 100 frames, I'm going to go through 1 cycle, right? So this wave's going to travel through cycles. So I'm going to do 200 frames for this. So view, animate. I'm going to do 200 frames at 10 frames per second. Highlight this. And hit animate. Okay, and this is the real and imaginary component of your wave. Okay, so that should complete 2 cycles for the entire animation. Okay, and if you want to plot psi squared, what would it look like? So if you want just the absolute value of psi xt squared, okay, so divided by the right unit over m raised to the -1/2, and there's your psi squared right there, the green line. You can see it's constant throughout the entire interval. Okay, and And that's because, what did we say? Psi star psi is just equal to 1. It's 1 everywhere. Okay? And remember we said this function, because of the way the cosine and cosine functions oscillate, it's not normalizable in the traditional sense, because it doesn't go to 0 as x goes to positive or negative infinity. And of course we say, and the reason that happens is because this is an unbound system. There are no restrictions on it. Okay, and we also said that because of this, there's no energy quantization. Okay? You can have any amount of energy, but in real systems, you're gonna have boundary conditions. Okay, and you're gonna have quantization. You'll have quantization of energy.
Could you scroll up to the equation?
Yes.
And I wanted to see the one on mass, because that was a question right all the way up
All the way up. Yeah.
to mass. Where you found the mass of the particle.
Uh-huh. What about the mass? A little bit more.
Yeah. Okay, so you just divide the
4 grams per mole divided by Avogadro's number per mole.
Yeah, but why did it come out in kilograms?
Because MathCAD automatically converts it.
Okay, so in order to convert to kilograms, we just have to divide that number by
Yeah, because if I want
again, right?
Yeah, because if I want the mass in grams, I can just say mass equals, and then I can tell it I want the answer in grams. So there's the answer in grams.
Okay, because I was there's a question like that in the whole right hand.
Yeah, you have to actually manually do it yourself. But the nice thing about MathCAD is it's units. The word for it is it's units aware. So if you know MathCAD knows the answer in a particular unit, you can ask it whatever answer you want in any other unit. So you don't have to specifically do the conversion factor. Look, this is in grams, right? I can convert this to kilograms. I can say there's 10 to the negative third grams in 1 kilogram, right? 10 to the negative third kilogram per gram, right? It doesn't change anything. Same answer. All right. So there's a website at colorado.edu, PHET, Interactive Simulations. Okay, you've seen this website before, right? When we did the photoelectric effect. And if you click on physics and quantum phenomena, you get to this quantum tunneling and wave packets. Okay, so this really explores the one particle problem with all sorts of different possibilities. You can have a free particle, and you can put potential barriers so that you can have restrictions on your wave function. And I have that program already running right here. Okay, so for example, if you click on plane wave here, you get the stationary state. Okay, and that's the real part, and there's the imaginary part right there, given that there's a potential bump right here. Okay, so if I want to make this a truly free particle with potential being 0 everywhere, that's the function we just plotted on MathCAD, right? So if you play that, and that's what happens to that wave over time. Okay? And then what happens is, let's say you want to put a barrier. Okay? So if you raise this part, what happens? And then let's say if I make my total energy, this green line right here is the total energy, and this purple curve right here is the potential energy. Look what happens if my total energy drops below the potential energy. Look what happens right here. What happened? The amplitude of the wave function drops, right? Exponentially. Remember your solution to this differential equation. You have e to the sx, and your s was ik, right? Because s had to be a square root of a negative number, and that's what causes the oscillation, the sine and cosine. But over here, when you have potential greater than the total energy, this s is going to be a positive. It's going to be a negative number, so your function is going to be a real number, and normalization requires that this one will drop off, goes to 0 at infinity. Okay, so you have what's called here a potential barrier. So whenever your potential energy is higher than if your energy is less than potential as x goes to infinity, you'll find that your wave function goes to 0. Okay. But one thing that's really strange about this, we'll talk about this when we get to tunneling, is that there's actually a finite probability of having the particle have a potential energy that is higher than the total energy. And that's contradictory to what you learn in classical mechanics. You say total equals kinetic plus potential, right? So you should always expect potential to be less than the total in classical mechanics. But in quantum mechanics says there are certain cases where there's actually a probability that you might find your particle in a situation where its potential energy is higher than the total energy. And so that phenomenon is called tunneling. So we'll deal with that more in another lesson. Right here is the probability density function right here. Okay. So this area right here gives you a probability of finding the particle in what you would call a classically forbidden region. We'll deal more with that next time. And so in our next lesson, we're going to talk about the particle in a box. And so we're going to make it a little bit more realistic. So we're going to put our potential, our particle, just like this, inside a box. So we're going to have a barrier. We're going to examine what happens if the particle is in this box right here. So we're going to call this x equals 0 right here and x equals L. And what we're going to do is we're going to make this box something like that. We're going to make this potential energy function go to infinity at the edges of the box. Oops, what did I just do? We're going to make your potential energy function go to infinity at the edges of the box. So what will happen is your wave function has to approach 0 there, and it's going to be 0 everywhere else. And so you'll just have a function inside. That will be your particle in a box problem. That's going to be our next lesson, which has already been pre-recorded from last year. So this is the last recording for this year. So starting next time, I will expect you to watch the video ahead of time. When you come to class, we will be having just quizzes and problem-solving sessions. Okay? We're going to be flipping the classroom from here on for the particle in the box and beyond. And let's see. That's it. So we answered all of these questions, right? And so if you need a review or a tutorial on solving differential equations, particularly the ones we've been dealing with here, these are some videos that you can look at.